Case study 3.3 looks at geothermal energy, and it turns out that geothermal energy is going to be a very important part of our future. And there are two primary types of geothermal energy. There's low temperature geothermal, and low temperature geothermal uses a heat exchange system in the ground, for example, outside your house in the backyard, and that stabilizes the temperature against which a heat pump can operate. And you can drive a heat pump either from the air temperature outside, as we used as an example in case study 3.2, or you can stabilize that temperature by using the ground temperature and either heating or cooling off of that set temperature. The key point is that by coupling this to a heat pump, you can stabilize the efficiency of this essentially year-round. But the other type of geothermal energy is high temperature geothermal, and this takes a number of different forms. The first and the most direct way is to use volcanic lava to create the high temperature that's required to create steam that can then drive a turbine to produce electricity. And this is used, for example, throughout Iceland and many other cases where large volcanic activity is the rule of the day. Another approach is to use hot sedimentary aquifer sources. That is very hot water underground where you pump cold water down, pressurize it, and extract the high temperature water, and again you drive a turbine that produces electrical energy by virtue of the steam produced by that high temperature geothermal. And then a third way that's becoming very important in both the United States and China is enhanced geothermal systems. And this one is remarkably simple. You drive cold water down through a pipe, not into a liquid aquifer, but into hot rock that exists below the Earth's surface. This is heated by radioactive decay, and then you extract that high temperature water again to drive a steam turbine. And so these different methods turn out to be very important. So let's look at how this is actually done. And this discussion is applied directly to the United States, but it's also true of China and a number of other nations. And that is, if you drill down and you plot the temperature that you reach, particularly of the temperature of the rock that you reach, 3.5 kilometers of drilling depth, which is actually, it sounds like a lot, but it's actually quite small in the capabilities of technology. You begin to hit temperatures of 150 and occasionally 200 Celsius. If you go down 6.5 kilometers, you start running into temperatures of 200 and 250 Celsius. And if you drill down 10 kilometers, you find large regions that are at a temperature equal to or greater than 300 Celsius. Well, you bring 300 Celsius water up to the surface, that will drive a steam turbine with great efficiency. And so west of the Mississippi, the United States has massive resources in geothermal. This is also true of China. So let's just review the way this is evolving. The simplest way is to inject cold water down 8 to 10 kilometers, let it diffuse through the hot rock formations, and then extract the steam coming out of that at typically 300 degrees Celsius, and to use that to drive the turbine that then produces the electricity that's added to the national grid. And the advantage of this is that it uses this general capability of extremely high temperature rock structures below the surface that exist in large regions of, for example, the western United States.